Um, this is the last presentation, I guess, of the summit. So, yeah. so, so good news is that we have all the time we can take. No, I'm just kidding. Yes. So, um, I was struck by that all throughout the summit. You have seen a lot of presentations, focused on um, acceleration, high power 9, high memory bandwidth. We have machine learning and, deep learning. And most of these applications rely a lot on I/O part. So my presentation is based on introducing to you Power 9 I/O infrastructure. We do have um, accelerator-specific interfaces, which are much more, you know, uh, suited for accelerator attachments, also some I/O. But the truth of the matter is that vast number of devices get attached in the system through PCIe. So this presentation is focused on PCIe attached I/O. So I'm going to give you a kind of overview, then how we differentiate ourselves, Power 9, against x86, even most modern x86. We also, it is less covered in the presentations that although we have PCI Gen 4, which doubles the bandwidth, still we also improved upon latency of I/O transfers on PCI bus. So I have some data on that. I think you'll find it interesting. So I'll start with a bit of history. We had Power 7 Plus. At that time, I/O bridge was actually a discrete component to the separate chip, attaches through memory GX bus of the system. And then we had PCI slots from that, and that was PCI Gen 2. In Power 8, we did two major enhancements. One is that directly integrating the PCIe root complex into the processor chip itself. That gave a pretty good latency and performance boost. And also PCI Gen 3. And CAPI 10 got introduced also. But in Power 9, we truly took a big step in the I/O space. So one is that, of course, we kept directly integrate PCIe into the processor chip. But we actually have leadership PCIe standard with PCI Gen 4. And in addition, we also did enhancements that improve the latency. So full cache integration. So meaning when a small packet is coming in, in Power 8, it will, if the cache line is not right, if it is dirty or it's partial, things like that, then we went through a long cycle of, I/O to going to memory, syncing it up, back and forth. So that introduced quite a bit of latency. So we have done cache injection, which is very helpful, and we see the results. So I'll just review for you, with the Power 9 I/O. This is a typical, I picked the IBM machine type 9006, code name ZZ system. So it has two Power 9 processors, and you can see number of PCI Gen 4 slots, and these are real PCI Gen 4 slots. We also, if you need expandability, we have switch and you can see in the picture on the right bottom, so we can get more slots. Current systems have PCI Gen 3 switch, but we will have later on PCI Gen 4 switches. So with PCI Gen 4, you get double the bandwidth for the same number of lanes, because it's a 16 gigabit per second per lane. Also, as you have seen coverage in the summit, we have high performance accelerator buses that are constructed using 25 gigabit lanes with NVLink 2.0, CAPI 2.0, and CAPI 2.0 is actually still on PCIe, but it still doubles because now it got PCI Gen 4 underneath.
I have a question. In some of the other presentations, they were talking about OpenCAPI 3.0. Is that shipping now on the current P9, or is that a future enhancement?
It's a future enhancement. The main reason is that the number of lanes is fewer right now, but it will get increased. So.
But is it retrofittable to like the AC922? Is it like a microcode update, or how will that happen?
Yeah, that's a good question. Let me get back to you on that. But because it's something in Power 9, I think should be possible, but there may be some limitations, so I want to check on that. Okay. So as I said, that we also improved the latency part, and I have some data to share with you on that part. In addition to bringing the I/O infrastructure improvements, we also working with partners to bring, higher speed I/O adapters supported. And we are currently shipping a 100 gigabit, 40, 20, 20, 10 gigabit InfiniBand and Ethernet adapters. These are RDMA capable, and this is Malinas Connect X5. And this is actually a PCI Gen 4, truly PCI Gen 4 adapter. And I have a use case coming up. I'll show you in a minute. But the good news is that PCI Gen 4 ecosystem is growing very fast. We have partners already working on, such as Cavium is working on PCI Gen 4. We're working very closely to get the PCI Gen 4 networking adapters that can do up to 200 gigabit per second, introduced quickly. Similarly, we're working with Broadcom to get, again, more PCI Gen 4 adapters, introduced on storage side and networking side. In addition, we also are working with partners to get PCI Gen 4 switch. So that gives us more fan out, more options to attach. And one project we are working on is to have a large number of NVMe devices connected using PCI Gen 4 switch to the system without oversubscription. Because in industry, you will see systems with 24 NVMe device, but when you dig down, you see actually it's not 24 NVMe worth of bandwidth there. We also have 32 gigabit fiber channel. We actually released it. It's available. And other we came up with this new design point for our Power Enterprise server is embedding NVMe devices in the planar itself, very close to planar and devices. So those are available. CAPI 2.0 flash and NVLink flash GT Plus and Volta card. So we have a devices taking advantage of this infrastructure. So this is the demo we did for Flash Summit. And in this one, we had Power 9 servers acting as a target server and initiator using NVMe devices, but over 100 gigabit Ethernet and PCI Gen 4 networking adapters on the both sides. So we had to put in 2 PCI Gen 3 by 8 devices to fill the bandwidth supported by PCI Gen 4 by 8, one adapter. So it kind of shows the advantage of that. And this actually, when we measured it, we got the full bandwidth, 100 gigabit per second with that. So like a real use case, and you can see, PCI Gen 4 helps a lot. Okay, let me talk about latency a little bit. So as I said, we improved latency, and we wanted to test it out closely to see how competitive are we with against um, x86. So we wanted to make sure we do a very fair comparison. So for that reason, we had a FPGA adapter. And what that adapter will do is basically turn around data from the host to that. So we get both direction. Very simple workload because we are focused on just the PCI latency part of it. And basically, it simulates the communication over the bus. Uh, and we didn't want to rely on the clock of the CPU or anything because there are always variations. So we actually use PCI analyzer trace to see when the transfer is actually occurring. And response times and statistics were measured. So anyway, so this card was used. So when we did the numbers comparison on Power 9, we saw that, our transfer CPU turnaround time is like 337.3 nanosecond. So I want you to focus on two ways. First of all, it is better than best on x86 from Kaby Lake. But more importantly, just see how the low this number is. So you can see the bus transaction, we're not consuming much latency. As long as you're hitting the cache, it comes out very good. The other bigger number point is that you see our standard deviation is very low. So we don't kind of, change over a lot of it. So the question is, once you have this low latency, what are the use cases? And as I was saying, there are lots and lots of possible use cases, but having low latency networking can give you lots of benefits. By the way, you will get the lowest latency if you use protocols like RDMA protocol, because that's our kind of, but unfortunately, those are not as interoperable. You have to have the same protocol on both ends. Not as widely deployed, interfaces are complex. Most of the industry runs over TCP/IP networking. So even there, we benefit from it. But the case we did was, we are, as you saw earlier, we have lots of high performance databases, GPU, in-memory databases. So we used to have sort of network latency didn't used to matter because the I/O was slow. But with that, these high performance databases, we have high performance number of transactions they can support is very large. So given that, we need good latency on the network side also. So on Power 9 especially, as you saw earlier, we have lots of success with high performance databases that are accelerated because we have a high memory bandwidth, we have accelerator attachments, which is world class. And so basically, we have a ideal infrastructure. And examples are Redis, Memcached, HANA, Kinetica, Neo4j. We had MapD, and basically lots of databases are there that could use with high transaction rate. So we do show we can increase throughput by using low latency networking. Now, you can do low latency networking with TCP/IP number of different ways. Just have a very tuned stack, a lot of acceleration you can do. There are specialized stack. There is open source DPDK. There is SolarFlare Open Onload. So the one we tested with is Open Onload. This work is sort of just starting, so I have very initial data. Still, it was fairly good. I want to show you that. So just a kind of little bit background. This open on load stack is actually very straightforward. Rather than using kernel-based TCP/IP, it uses the user space TCP/IP, and it still maintains the sockets interface. That's the claim to the fame, that you can take same application and just run it in open on load stack, and you don't have to make changes. And this is for sockets applications. So this way, and it doesn't have to be running on the both ends. You could be, server side could be this, and the other side could be standard TCP/IP. So kind of good use case for doing the latency. So when we did this test, it's literally out of box running on P8, and you can see we got 50% improvement on number of transactions, and with good reason, because the typical latency using this kind of technique is of the order of like 2-3 microsecond, and we compared against Intel adapter, 10 gigabit adapter, but the difference being open on load versus that, and we got 50% transaction improvement. That's pretty big deal, especially in database world. So anyway, so this is just one example of, once you have good latency, what you can do, but you can do, many other things, whether it's a GPU scaling using your Horoward or TensorFlow, when you can take advantage of it in your HPC applications, of course. So we are pretty excited about having that low latency also. Now we have a competitive one. Okay. So that's what I wanted to cover. Are there any questions? Okay. 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 Thank you guys for.
I do have one question. You had mentioned early on NVMe.
Yes.
So the new NVMe adapters for the NVMe disk packs, they're all going to be Gen 4?
Current technology that's available from partners is actually Gen 3.
Okay.
But again, we're working with partners, can't disclose and all because of their confidentiality, that are going to be Gen 4.
Got it. So
Okay.
that's a future.
Yeah, that's a future thing. One thing that does remind me that Cavium has a kind of solution called NVMe Direct, right? Which kind of can take the data directly from the network and kind of transfer to the NVMe. So that gives again a very good target side solution. So.